Hi everybody, it's Sophia here, and today I'm going to be going over our Seattle INTEGIRLS Spring competition for our middle school division, and I'm going to be going over problems 6 through 10. So if you haven't watched the first part, which covers 1 through 5, I recommend that. But yeah, let's just get started. So starting off with our first problem, I can probably size this up for you guys. But it says, how many anagrams of the phrase "I'm fearless" contains the letters F-L-A-I-R in that order? So ignoring this condition, let's just figure out how many ways can we order "I'm fearless." So just writing this out, we have I-M-F-E-A-R-L-E-S. And so how many letters do we have? Well, we have something like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 letters. So if we just rearrange that, that's 10 factorial. However, the issue here is that we might have repeat letters. For example, our repeat letters are E, and our repeat letters are S and S. So since we have two letters repeating twice, we divide by 2 factorial. And if we do compute this out, this gets us something like 907,200. We don't need to compute it out, but you can if you want to. And the reason why you don't need to compute it is because of our condition, which says that we want F-L-A-I-R in that order. And so out of all the ways we can arrange F-L-A-I-R, that's 5 factorial. Only one of them is going to be the order that we want. So what we do actually is we take this original number and we just divide by 5 factorial, because we know that out of all the 5 factorial options, only one of them will give us the one with these letters in that order. So if we do end up doing this, then we get something like 10 factorial divided by 2 factorial times 2 factorial times 5 factorial, and this gets us something like 7560. So just dividing this by 120 basically, and that's our final answer. Oh, I just realized my screen is covering this. Let me scroll down here. But yeah, hopefully this made sense. We just find the total number, and then we find what fraction of all our possibilities will have what we want, and it's 1 out of 5 factorial. Nice. Moving on to the next question. When an ice cream truck arrives, 12 people, including Bonnie and Charlie, stand in random order in a line. Bonnie's extremely impatient and decides that if there are more than 3 people in front of her, she will skip the 3 people directly in front of her in the line. The probability that Charlie ends up at the back of the line can be written as m over n. We want to find m plus n. So in general, the probability that Charlie is at the back is just 1 over 12. Because there's 12 positions, and if he wants to be at the back, that's 1 out of those 12. However, the trick here is that there's this case where Bonnie will skip in line, and then Charlie might end up at the back. And so that only scenario where that will happen is if Bonnie is last, and then Charlie is before her. And this makes sense because if Bonnie's last, then she's going to skip up 3 people. So then the last place is now going to fall back to Charlie. So what is this probability? Well, this probability, the probability that Bonnie is last is 1 over 12. And the probability that Charlie is right before is 1 over 11 because we have 1 less space. So now all we need to do is just add these 2 up. So 1 over 12 plus 1 over 132 looks something like 12 over 132, which is something like 1 over 11. And since they ask us what m plus n is, 1 plus 11 equals 12. And this is our final answer. Our final answer is 12. So hopefully that made sense. We only have 2 cases. Either Charlie's already last or Charlie only becomes last once Bonnie moves up. Okay, moving on here. I actually don't know how to pronounce these names. Bill Blaine has discovered a marvelous new variety of mango, which he is eager to tell his town of Scolandia about. Every day, every person who knows about the new variety of mango will randomly, with even chances, tell either 6 or 7 new people about it. Even though he knows about this randomness, Bill Blaine is absolutely certain that it will take exactly 3 days for the entire town to know about it. How many possible values are there for the population of Scolandia? Okay, so what's going on here is we are essentially given a range. So there should be a range that the population falls under, right? And what's really interesting here is we kind of have a minimum case and we have a maximum case. So let me get into this. Minimum case is if after day 3, every person only chooses 6 people to share. So if we add this up, we end up getting something like 1 for the first day, or day 0, I guess. The next day is going to be plus 6. Then we do 6 times 7, and then we do 6 times 7 squared, and then our days are over, 3 days are over. So then we get something like this, and spoiler alert, if I add this up, you get 343. And then, similarly, we also want to do our max. And our max is only after 2 days instead of day 3. And this is where each person chooses 7. So now we have something like 1 plus 7 times, plus 7 times 8, excuse me. And this gets us something like 64. So now we have our range. But the question is, how many possible values are there? So we want to figure out how many possible values lie between these values, because we have our max and our min. So in order to do that, we do 343 minus 64. And sorry guys, my mouse. This gets us a final answer of 279. So that's our final answer. So as you can see, we just do a minimum and a maximum, and we say, okay, assume in this worst case scenario, everyone tells 7 people or everyone tells 6 people. Nice. Okay, moving on, we say how many 3-digit numbers are neither multiples of 11 nor palindromes. So here we have kind of a casework scenario. And one thing we can do to approach this question is think about it through complements, which means we can do a kind of smart strategy instead of trying to count everything. So what we do is let's just take all the 3-digit numbers, and then we subtract the numbers that are mults of 11 or palindromes. So the first thing we want to do is find out how many multiples of 11 there are. And so we know that the first multiple of 11, that's 3 digits, is 110, and the last is 990. So if I subtract this and I divide by 11 and then I add 1, we get 81. So that means there's 81 3-digit multiples of 11. Then I want to count how many 3-digit palindromes there are. And if we look at if we think about palindromes, we know they must be in the form of ABA. And we know that there's 9 options for A, because it can be either 1 through 9, and then there's 10 options for B, because now it can be 0 through 9. So this gets us 90 palindromes that are 3 digits. So now I want to find, okay, well, how many numbers are both? And so a palindrome is divisible by 11 if and only if its alternating digit sum is divisible by 11, if we think back to our divisibility rules. So this means that we want, let me find a different color. We want 2a minus b to be congruent to 0, mod 11. So it's either 0 or 11 or something like that. So, continuing on, we can just count this. So, if 2a minus b equals 0, then we have b equals 2a. So the options of a are 1, 2, 3, 4. Then the next scenario is here. 2a minus b equals 11. B equals 2a minus 11. So a is going to be 6, 7, 8, or 9. In total, though, this is 8 options. Hopefully that's clear. So that means there are 8 palindromes divisible by 11. So now what we do is we use something amazing called the principle of inclusion-exclusion. Its acronym is PI, principle of exclusion or inclusion, exclusion. So in order to do this, in order to find what we wanted, we first find the numbers that are multiples of 11 or palindromes. And so that is our multiples of 11, which is 81 as a reminder. Then our palindromes, which another reminder was 90. And then those 8 that we found that are neither, or are both, excuse me, to find 163. But again, we are doing our complementary counting. So we take our total number 3-digit numbers, which is 900, and we subtract by 163. So this gets us 737. So that means our final answer is that the numbers that are neither multiples of 11 or palindromes, how many are there? Well, there's 737. So yeah, hopefully that made sense. We use the principle of inclusion-exclusion as well as complementary counting. And then finally, moving on to our very last problem here, we have something of a geometry problem. I think this might be our first one in this set, actually. So one thing we can think about is, or first let me read the question. Points A, B, and C are randomly chosen on a circle. The probability that the minor arc AB is at least twice the length of the minor arc AC can be written as x, y for positive integers, for integers x and y. Find x plus y. So we can just assume that A is fixed on the circle. So A must be here. And then B and C are chosen randomly, independently and uniformly. And so now essentially we can say, I'm just going to draw a random B and a random C. But let's say we call AB X. And let's call AC Y. Then we know that since the minor arc is always the shorter arc, both X and Y are between the interval 0 and pi. And so the problem essentially becomes, if we use X and Y, we pick XY from this range, 0, pi squared, and we want the probability that X is greater or equal to 2y. So this is just an area problem now. So this looks something like y equals x over 2, and we know that x, is less than or equal to pi. So then we can say that y is less than or equal to pi over 2. And so then our desired area or region is essentially just a triangle that looks something like this. So it has the coordinates 0, 0, pi 0, and pi over 2. And this triangle we can find the area of relatively simply. This is just 1/2 times pi over 2. And if we do expand that out, we end up getting pi squared over 4. And the whole square has an area of pi squared. So our fraction is now something like pi squared over 4 all over pi squared, which simplifies down to 1 over 4, and that's our final fraction. So we find something like x over y equals 1/4. And if we know that x over y equals 1/4, our question is just what is x plus y? So our final answer is going to be 1 plus 4 equals 5. So yeah, that is how you do question 10. You can kind of convert this into an area problem. So if you are ever unfamiliar with something, try converting it into something familiar. And yeah, that concludes the second part of this solution series. So hopefully this made a lot of sense, and make sure to check out the first part if you haven't already. But other than that, that's it. So thanks for watching.